welcome to the people from the Branford group. Thanks, Will, for joining. Thank you, Jack and Kilian, for taking the time to give the talk. The talk will be delivered in two parts. We will have, correct me if I'm wrong, Jack, but there will be an introduction of artificial spin-vortex ice systems by Dr. Jack Gartside, who is a postdoc at the Branford group, and will be followed by Kilian Stenning, who will describe reservoir computing to us, and who is a PhD at the Branford group. So the title is Reconfigurable Training and Reservoir Computing via Spin Wave Fingerprinting in an Artificial Spin Vortex Ice. So when you're ready, let us start. Thank you very much. Look forward to the talk. Yeah.
Brilliant. So yeah, thank you very much for the invite. I've been looking forward to this, and it's a pleasure to share all our research with you and meet you, and I'm looking forward to the conversations that we'll hopefully have after this. So thanks for the introduction. I'm Jack Gartside. I'm currently a postdoctoral researcher in the Branford group at Imperial College, and we also work closely with the group of Hide Kurobayashi at UCL. So this is very much a collaborative work, so I'd like to start off by talking through some of my collaborators here. So Kilian Stenning did a fantastic job at implementing the reservoir computation scheme, which is, I think, the real reason that a lot of us are excited about this work. Alex Vanstone, our other PhD student, is currently writing up, did some great work showing how the FMR fingerprint, if you like, the spectra taken near remnants, can provide a really good readout of the microstate without having to do MFM or beamline experiments, and he showed it can reveal maybe more information than people had previously realized. Troy Dion has done some fantastic spin wave simulations for us. Holly Holder is our very recent PhD student, has done some of the great MFM imaging. Francesco Caravelli is at Los Alamos National Lab and helped us with some of the theory behind reservoir computing. And then Dana Rue, who has worked with both Will and Hide, has provided some good theoretical grounding. So the image we have here, just to show you what this thing is a MFM picture of one of our artificial spin vortex ice systems in a mixed state. And you can see the macro spins. These are your spins of the spin vortex ice here, with your traditional kind of North Pole and South Pole light and dark magnetic charges. And then you have our vortex networks, which are these more kind of squidgy, my friend says they look like those table biscuits that you get with cheese. So you can see the kind of interesting domain patterns that come around when we've engineered both of these textures within our systems. So I'm gonna give you a quick sorry, I'm just trying to hide the picture of myself so I can see my slides. A quick run through of what we're going to talk about today. So I'm going to give you an introduction to artificial spin systems, from the more simple artificial spin ice up to our current system. Show you why the issue of microstate control in these systems has been a pressing one in the field, and some of our prior efforts as a group to address that. Then we're going to look at how we've modified spin ice to be able to support this bitextural property of having the vortex as well as the macro spins. Show you a trick that we came up with to have a ratchet-like field cycling, which gradually converts those macro spins to vortices. Look at the FMR signatures of both the macro spin and the vortex modes, and then show how we can use FMR to reveal this emergent physical memory property where we can train the microstate of the system over large amounts of field loops, so still seeing differences up to 60 field loops. We're then going to show you how we can insert vortices manually to any site we want via an MFM tip. And then Kilian's going to follow up with a reservoir computation scheme. So to start off with, what's an artificial spin system? So originally, these were intended to mimic some very complex spin structures that occur in synthetic minerals. So you may be familiar with the one called spin ice. So you get things like dysprosium titanate, where you have these very complex, convoluted, three-dimensional spin structures in a bulk material. So these exhibit geometric frustration similar to that of the proton placement in water ice, hence the name spin ice. So at each vertex, you are trying to satisfy two spins pointing into the vertex, two spins pointing out, but there are multiple ways which are energetically degenerate, in which you can satisfy this. So this leads to a residual entropy at 0 Kelvin and a number of other interesting properties. One of which is sometimes you get spontaneous breaking of this rule, and these vertices where you break it can behave similar to magnetic monopoles. You have interesting things where you get flow of these effective monopoles. People call it magnetricity. Now, all of this interesting bulk properties come down to the microscopic arrangement of the spins. But of course, within a 3D bulk material, these are really, really difficult to interrogate and, effectively invisible. You can infer them and do neutron scattering, but you're never going to map out what every spin is doing in the system. So some people thought maybe we can make an analog. As nanoscale patterning was getting more and more sophisticated and the imaging of the magnetic state of such nanopattern systems, people wondered, how coarse can we go with our approximation of, nanopatterning something that just kind of ticks the same geometric boxes as these minerals? Can we get them to show the same bulk extensive properties while at the same time being able to measure really what these spins are doing? And somewhat fantastically, I'm still stunned by it after 9 years in the field, you really can. So this is artificial spin ice. People just pattern really simply bits of permalloy typically. We're looking at bars of, these are about a micron long. The stuff we look at these days is, goes down to as short as 200, and people do really tiny things. So it's nano to micron scale, usually between 5 and 20 nanometers thick. And here's a SEM image of the lattice. And then on the right-hand side here is an MFM image of the same region. So I've put in false color with these arrows to show you that spin flows from a dark charge to a light charge on each of these bars. And amazingly, that same residual entropy, the same monopole defects are observed when you pattern one of these things. Now, you also have all of the great freedoms that come with nanopatterning, that if you can stick it in a CAD program, you can realize it. So here is a really fantastic bit of work where a group in Leeds that I used to be part of for my master's have realized a Penrose tile artificial spin ice. And it doesn't just look pretty, but a whole bunch of kind of macroscopic emergent properties arise that you don't get in this type of spin ice. So not only can you make these beautiful things, you can also design in whatever emergent dynamics you can, come up with at your theoretical physics table. So, the great promise of these things is you have this huge microstate space. So you have n bars. For us, m can easily be 100,000 or a million, and you have 2 to the n possible microstates. So there was a lot of the writing about these systems in the early literature, and still to this day, people talk about it in the introductions, and the conclusions are, there are these specific microstates that have these fascinating properties, both from a fundamental physics angle, such as the monopole excitations I mentioned earlier, or they have very elaborate large-scale ground states, which are quite rare in physical systems. And if you can access these, you can both learn a lot, and also some of these states have really exciting functional benefits, both for data processing and storage, and also for reconfigurable magnonics. So you can imagine one microstate might act as a magnonic transistor, another as a bandpass filter. And there's been a lot of theory work showing that these things look really good. The problem is, how do you prepare one of these microstates? So, it's very simple to prepare a state like this. And typically this is what people do. You whack a big old magnetic field on it such that every single bar is pointing the same direction. Not very exciting and not very useful. That state doesn't have much going for it. And, if you want to come out of your 100,000 spins to spin number 700 and reverse only that spin and nothing around it, it's a big problem. So what people started to do in the field is some very kind of rough rudimentary tricks to get to a few different states. So you could put a field on, you could run a kind of degaussing protocol, and you exploit the fact that because you're nanopatterning, these aren't perfectly, all of these spins aren't perfect copies of each other. One of them might have come out 1 nanometer wider, one might have a tiny bit more oxide. And as a result, you have slight distribution of coercive fields. So as you degauss them, certain bars get trapped pointing one way while others flip. And you can get these kind of like randomly demagnetized states, but you can never re-prepare the same thing. You could also heat them up and thermally anneal them, but that has its own challenges in being able to heat them up without wrecking magnets. You have to make them really small, and then they get hard to image. So you've kind of lost that benefit of coming to an artificial system. So this is one example from, again, that group in Leeds that I used to be part of, where they have grown the system on basically in a hot stage, and they've managed to grow it into its ground state. So this is an example of those kind of elaborate states. You see here, you have alternating loops of alternating chiral loops, which serve to close each other's flux. So other than that, people were kind of scratching their heads. So this comes to the work I did during my PhD. We noticed that if you took a strong enough MFM tip, and this doesn't have to be anything special, we just bought a high moment tip from a normal supplier, and you run it across a nanowire, the field of because the field of the tip radially points outwards, I'm just going to try and play that animation again, you can see that it induces this vortex in the middle, which is a topologically protected defect in a continuous nanomagnetic system. And where you bring the defect in on one side to balance out its +1 topological charge, you lock this pair of half integer bound defects on one side. When the vortex gets to the other side, you now have to compensate for losing that +1 charge, and you put in another pair of +half edge bound defects here. Now that is the topological description of something called a 360 domain wall. So don't let the language of topology scare you. Basically, all it means is if your tip's strong enough, this has to happen. It's really robust against different materials, different kind of nano fabrication imperfections. And we got quite excited about this. So, no one's that interested in 360 domain walls. They had some niche applications, but if I play that one more time, last time I promise you, as you put them in, look at this bit here. Do you see that it pings off? So because it formed in a really contorted way, it's got this, you can view it as treating the exchange energy a bit like a kind of elastic potential. I think of it as, when you're playing pinball, you're kind of pulling the thing back, and then when the vortex gets to the end, you let it go, and one of those domain walls is shot off. So first of all, we saw this in theory. I'm just going to show you that it's real. So here's a bit of a nanowire. There are no charges, so all of the spins are in the plane along the long axis. We put a big, strong high moment tip on, and this dark contrast here was the signature that told us when it was strong enough. So we scanned along, we're like, right, we're getting this injection, we're seeing the dark contrast. I retracted the tip where the triangle was and imaged again, and this is what a 360 domain looks like. You've got your head-to-head bit here, tail-to-tail bit here, so it works. And going back, so that was in a really long quasi-infinite wire. Now, as I showed here, where these things spread out, we started to think, hang on, no one really cares about 360 domain walls as much as that hurt our feelings. But if you could get a wire that was short enough such that at the apex of this domain wall separation, the attraction between the domain wall and the charge on the wire end overcomes the attraction between the domain walls in the middle, hey presto, you've got a method to reverse that magnet number 700 within your 10,000 magnet network. So again, taking it out of our heads and into the real world, here's an array of wires, different lengths, that I saturated all pointing one way, came along with the tip, and hey presto, they have all reversed, which is a really exciting day in the lab. So we wanted to show it's not just kind of straight lines, you can put in these more complex states. And then, our group's a spin-ice group. Can we take it to the real proving ground, which was the strongly interacting nanomagnetic arrays? This got harder because as you're reversing one bar, it's not isolated anymore. So the bars here are far enough away that they're not really affecting each other's state. So here, the bars really do care about what their neighbors do. These monopole excitations here. So we call it monopole because you've got 3 north poles in here, and they're basically either effectively like a total sink or a total emitter of magnetic flux. They are really energetically unfavorable. As anyone knows, if you try to hold like magnets together, there's a big energy barrier. So we tried to write one with our tip, and it managed to do it, which was exciting. So then you start to try and write these other states, which are, you can get these things if you randomly anneal your system. They're very rare, but they happen. However, something like this, where you've done the kind of nanomagnetic thermodynamic equivalent of roll, 10 sixes in a row, you really can't get these by any other method other than writing them in by hand. So when I told you one of the other states of interest were these very large scale ground states, they've been seen in square ice, which I showed you before, that nice work by Jason Morgan from Leeds, where they've grown it hot. However, in a hexagonal or Kagame ice, which is what people call this geometry, the ground state is huge. It's 30 bars, and it's only very subtly lower energy than the energy of its other states, which are similar with maybe a few other bars flipped. So people have tried to anneal this, tried to prepare it for a long time, and they hadn't managed. So this is how it looked. You'd have to reverse all of these bars, and we managed to write that. So that was exciting. We then came to, so I guess a bit of perspective here. So one of the things that people have wanted to write these states for is they thought, if you could put state programmability in, you should be able to harness some of the really nice properties of these systems, that they have an intrinsic memory, they strongly care about what their neighbors do, and they also have some very non-linear dynamics. Those tick a lot of the prerequisite boxes for being good at neuromorphic computation. So when we saw this, we were like, right, maybe we can finally try something. But we realized we're doing this with an MFM tip. It's far, far too slow. Is there any way we can keep some of this functionality but scale it up so we can do it with magnetic field? So I drew this shape out on a napkin where I was thinking if you could use combinations of fields along X and Y. So the wide bars here have low coercive field, thin bars have high coercive field. You can now prepare not absolutely any state, but the four, what you could call pure microstates of artificial spin ice. That is, every vertex is doing something else. So every vertex in the system is doing the same thing. So this state on the left is the ground state in square. So similarly to what Jason Morgan did by heat, we can now just do by field. So if you saturate the system in one direction, so you saturate it to the left, and then apply a field to the right, such that only the wide bars flip, you get this. This is just totally field saturated. Then over here for the high energy states, you do the same trick as putting a big field in one direction, then a field in the other direction, such that only the wide bars flip. Here you do it in Y. So just with simple global fields, we're able to prepare this range of states. And where I told you that we were interested in using the system as a reconfigurable magnonic crystal to try to realize some of that functionality of, maybe you can filter at different frequencies, open up extra bands and modes. This was the work we did earlier this year, showing that, once you have greater state control, spin ice really starts to look like a better magnonic crystal. So what we have up here are the magnonic heat maps of the system in each of those four pure vertex microstates, which I told you about. And you can see they're really, really different. So you can imagine, say you wanted to have 3 channels open, you would put the system in a type 3 state, and now you have 1, 2, 3 modes. If you wanted to flip the gradient of your 2 modes, you could put yourself in a type 1 state relative to a type 2. And if you wanted to have up to 4 modes active at one time, even though they're faint, you do have that in the type 4 state. So a lot of reconfigurability on offer here. Now, it also let us, that's kind of functional side. Going back to the fundamental physics side, it also let us see something that had been really elusive. So people had thought in such artificial spin systems, you should be able to get the magnons present in one magnet, so let's say this magnet here, to couple to those in another magnet and hybridize and introduce distinct optical and acoustic bands with an avoided crossing or level repulsion. But no one had ever seen it, and people had given reasons, oh, maybe it's too weak, maybe these things just don't interact enough, or maybe because the magnons tend to be localized in the bulk, that's too far away. However, we showed in this work that the issue was you needed a broken symmetry at the vertex for the magnetic field. So in order to get the optical and acoustic modes to have the required opposite gradient, you needed this kind of thing. So you can see here when we have that broken symmetry, you get this split gradient, which isn't present. And like I said before, without these state control methods, all people were doing is saturating and sweeping. So the field had been doing this when they needed to do this, but without a trick like ours, it wasn't possible. So you can see here when we prepare that state and look around the crossing, you get these gaps here in the middle. And we've shown in our simulation, so they're in the paper, that if you look at this top optical band here, you have an out of phase relation between your precession in adjacent magnets, while at the bottom acoustic branches in phase. So we took this system and we were wondering, what else can we do with it? So, we're still not at the point where we're doing computation, and we'd really like to get there. And we felt, people had been trying to do this in SpinIce for 10 years, and a big part of the issue, people couldn't really picture how to do it. People had these simulation papers that show that you kind of could do it if you could kind of magically know exactly what every magnet was doing, but realistically, you're not going to have a computer with an MFM in it, and you can't run a computer inside a beamline. So when we were doing our spin wave measurements for these things, we started to realize we were getting more information out than people thought that you could. And while it wasn't as perfect as MFM in terms of giving you the knowledge of all these spins, maybe it could give you enough. So we were also interested in these physical memory papers that people were doing on spin systems, where you would loop the field again and again, and surprisingly, things kept changing. So there's a property called return point memory that says you might loop the field again and again and again, but rather than like if you run a lot of minor field loops on a thin film, you kind of keep getting the same thing. Your magnetization might go to, let's say, 0.8 of the total saturation, but it's going to stay there. In some cases, you can do it so you have oscillations of the magnetization value. Certain spins are basically getting stuck or exhibiting periodic behavior. So we thought, we've already seen a lot of rich microstate control offered by having the two thicknesses here. Let's try to do some looping. So here is the all macrospin state, kind of the type 2 that I showed you that people typically prepare. And here is the corresponding FMR spectra taken at near 0. So it's a -1 millitesla field, just gives us a tiny bit more signal to noise than absolutely 0. So we then ran 30 field loops at 18 millitesla. So the wide bars flip at 16. So every time we're flipping the wide bars back and forth. We took another spectra and it was totally different, which really surprised us. So you can see the thin bars untouched, makes sense. The thin bar coercive field's up at about 21, 22 millitesla, but the wide bar macrospin mode is gone. We've got this new mode down here. So we were like, what is going on? We MFM'd it and we saw something like this, similar to that image on my introduction slide. So you have some macrospins, but loads of these other things here. So we were a bit confused by this contrast. We thought one thing it could be is a vortex sat in the middle of your bar. So just by chance, Kilian had done a recent paper saying how vortices, if you could make a disk that was bistable between a vortex and a macrospin, it would be good for magnonics. So we had a little idea of how these things performed in simulation. And we simulated a vortex state and then used an add-on to Mumax to simulate the MFM contrast. And we saw that actually this kind of checkerboard pattern is what you expect. We then ran some simulations of the expected FMR behavior of a vortex, a bar of this dimension in a vortex state. And this broad mode down here is exactly what you get. So somehow our loops were converting the system from an all macrospin state to a nearly all vortex state. So it turned out, yeah, between you and I, we like to say that it was perfectly engineered, but it just so happened that the bars we made for the Nature Communications paper happened to sit right on this bistable energy line between the macrospin and vortex states. So the bars don't really care which state they're in, which allows you a lot of freedom by using this field looping to convert back and forth between the states. So we've got this initial state here, everything's macrospin, loop back and forward a bunch of times, and you see these mixed states here. So these kind of like wormy things are your vortices, and you can notice here that they actually tend to nucleate adjacent to other vortices. So we're also starting to see this kind of emergent collective dynamics, which is really exciting. So showing you a little bit about how these things form. We go from a saturated state like this, and every time you reverse, there is somewhere between a 1% and 3% chance, depending on what the surrounding bars are doing, that your reversal process will proceed as normal for macrospin flipping to an oppositely magnetized macrospin, but then about halfway, you'll see a reversal, and your topological defects on the edge will come together to meet at the end in the middle of the vertex, forming a vortex core, which is then topologically protected and effectively trapped inside the bar. And to push one of these things out, there's a big exchange penalty. So they're quite well protected up to a high field. So the vortices have significantly higher coercive field than a macrospin state in the same bar. We wanted to see under MFM exactly how do these things come in. We saw some really nice things here. So we did 4 loops back and forth at 18 millitesla, take an MFM image after every half of the loop. So the negative field, negative again. And you see here the vortices nucleating. They're kind of coming in randomly placed, and we repeated this, and they don't come in the same site. It is stochastic, but they're isolated, they're on their own. And then what we start to notice is as you keep looping and more vortices nucleate, you get an increased chance of the vortices that come in after nucleating adjacent to ones that already exist. So you can basically go into the micromagnetics, and it's to do with the field profile in the adjacency of an existing vortex. So the vortices don't really have much stray field. It's all closed within the magnetization texture of the bar, whereas macrospins put out a lot of stray field. And having that break in the kind of dipolar field landscape of your system encourages vortices to form. It encourages those topological defects to come together rather than staying on opposite sides of the bar. And you can see that as we go, these things form larger and larger chains, and you're starting to see islands forming of the remaining macrospins. We can take this out to much longer numbers of loops, and you can see that these domains, so for instance here, it's quite clear to see your macrospins, your remaining macrospins are clustered together, and your vortices are also clustered together. So you get this really nice new type of domain formation that comes in because you've engineered textural bistability into your system. So we also took heat maps corresponding with the states that we've shown here, and you see this really nice gradual introduction of this kind of highly nonlinear X-shaped mode. And what you're seeing here is the regions of the spin texture above, that's here, and below the vortex core resonating. And what's happening is the core itself is quite free to move within the bar as you apply field. So it'll move from one end to the other. And you can imagine it like a wine bottle that you're filling up or emptying liquid out from. As the vortex gets scrunched up, the mode above it gets smaller, so the frequency gets pushed up. Likewise, the area resonating below the vortex core gets bigger. And so you've got, less water in your bottle and a larger volume of air to resonate at lower frequency. So you get this very gradual emergence of it, which is quite rare in reconfigurable magnonics. It's usually you're flipping between 2 binary states. So this affords you a really nice analog control over your mode profiles. Just to show you some simulations here, we have, the curvature coming up here. You can see that quite nicely reproduced in Mumax 3 simulations. This is showing you the mode profiles. And like I said, you can see at 0 millitesla, the cores in the middle, you have equal volumes either side, and that's this point here. You don't observe the 2 different modes. And as we move from +5 to -5, the cores shift, and you can see what we've called M1A here, where it's large at +5, you get a low frequency, and then it comes up to a high frequency here as it gets squished up into the other end of the bar. You also get these higher order whispering gallery-like modes, which we do detect experimentally. You can see them in this checkerboard up here, maybe even more clearly watching that come in there. And it's quite interesting. You've got a much flatter dispersion relation because it's not related so much to the core position, and therefore it isn't moved around by field in the same way. So we wanted to now see, how rich were the training dynamics. where, you know, we said we've got this analog control of your macrospin population coming down. We've seen it in MFM. And what we've done here is we did 30 different field loops, taking a -1 millitesla spectra after each loop. And you can see that the macrospin mode gradually decays off. Doesn't only just decay linearly, it's also shifting down in frequency. And the reason for that is, as I mentioned before, your macrospins add a lot of dipolar field to the system, whereas these add effectively 0. So the average field felt by the remaining macrospins drops as more and more of them are turned to vortices, and you've got less of that dipolar field to push the frequency up. You also see that in the thin bars here. The opposite happens, they're shifted up because the remaining macrospins would have been opposing them. So yeah, the vortex mode comes in really nicely there. And if we look at the decay rates, we can see that we have a lot of control over the decay rates and also the final mode amplitudes, depending on what we do with our thin bars. So before, we said we weren't really switching these things, but if you hark back to the Nature Communications paper I introduced, I showed you that by saturating the thin bars in one way, you can either be moving into a ground state or into a high energy monopole state. So we found that if we trained our system with the thin bars in a ground state configuration, we got at first a very gradual increase in the vortex population, but actually by the end, kind of like a tortoise and the rabbit story, you get a higher vortex share. Whereas if you set your thin bars in the monopole orientation, your vortex population jumps very quickly, but saturates at a lower final share. You also see that these decay rates of the mode amplitude are different. So your thin bars can reconfigurably direct your training dynamics throughout the whole system. It also shows you, how sensitive the whole process is to the dipolar field landscape, because really that's what you're changing when you remagnetize the thin bars. So you can also turn it from a vortex state back to max spins. What we've done here is prepared a vortex state and we've swept linearly up in field. So you can see that this is the field that your remaining max spins flip at. They're jumping up there. And your vortices remain up to about 24 millitesla. So that difference in field is what allows the ratcheting that I mentioned. So you can loop back and forth here, and you'll never get rid of any of the vortices that you create. So that's why this window from here to here, you're free to cycle your field and continuously increase your vortex population. If the vortex coercive field was lower, none of this would be possible. And this is just showing as well, you can prepare different initial states. So this is 5 training loops, 10 training loops, 30, and then sweeping the field up. And you can see that we get these nonlinear sigmoidal-like curves of how your vortices convert back to your max spins. So this will be relevant for Kilian's section. When creating vortices, we have an exponential decay. When getting rid of them, we have a sigmoidal increase, and this asymmetric nonlinearity becomes quite important for the computation section. So finally, I'm going to show you how we can manually write these vortices in. So we're applying no field here. I've got an initially saturated state, and I come in with a high moment tip, the same trick that I showed you that we developed earlier for controlling all max spin ice. We've modified here to be able to manually write vortices. So here I put in one line, here I put in a second longer line. And now what we're interested in is, I've mentioned before that we've showed how the vortices can modify the local field landscape. We had a feeling that that would modify the effective coercive field only in the vicinity of the vortices. So what I'm doing now is field looping, but only at 13 millitesla. So the coercive field for one of these bars is 16 to 17. And you can see that as I loop, nothing reverses other than bars in the vicinity of the vortices that I wrote in manually. So we get some max spins flipping here, a whole row flips sandwiched between the written vortices. And then I apply just a negative field here and effectively heal, if you like, this disruption to the lattice and return to nearly what I wrote initially. One extra vortex is nucleated on the end there. So what we can do here, which is really fascinating, is manually come in and change the field response and evolution manually. And crucially, we can do that locally by putting these vortices in. So this also offers you a way, if you like, to future to the computation Kilian is showing you, potentially manually program certain dynamics into your lattice. So I'm going to stop here. I think it's a good time to hand over to Kilian because we're just getting into reservoir computation. So I'm going to stop sharing, and Kilian, if you'd like to take over.
Yeah, great. Thanks, Jack. Just share my screen. Cool. Can you see that all right?
Yeah, we can see. Thank you, Kilian.
Great. Yeah, so I'm going to talk through the reservoir computing stuff. And yeah, as Jack said, it's a massively collaborative work, and I won't go through all the authors again, but yeah, it wouldn't be possible without the contributions from everybody. So just a brief introduction to reservoir computing. So I think we're mainly familiar with the concept of deep neural networks, and these perform exceptionally well at a bunch of tasks such as image recognition or speech recognition and things like that. But they take a long time and energy cost to actually train these networks. So here's a little schematic. You have basically these neurons, and they're each connected to each other by synaptic weights. And so your training has to go through each of these weights and update them and then compare the result. And this, as I said, this takes a lot of time and energy. And while it's suitable for some kind of high-end tasks, it's probably not suitable for future like Internet of Things devices and things like that. And so what reservoir computing aims to do is kind of remove this training requirement by replacing your hidden layers in a neural network by this nonlinear dynamic reservoir. And in this kind of setup, you'll input your data into the system. The system will respond in some nonlinear way, and then you'll sample the outputs either in time or space at different points. And the advantage is that your training is now just linear. You just do a linear regression training method on your outputs. I'll go into a bit more on how that applies to our system. And so, yeah, there's a strong interest in trying to make these hardware reservoir systems, so that they've been around in software for some time now. But they're being performed on, conventional CMOS computers, which aren't really designed for this type of computation. So just to look at some previous examples in kind of artificial spin systems, there's some really nice work out there. Kind of looking at the different lattice configurations of artificial spin eyes. And one particularly nice work, actually, I should say that a lot of these schemes kind of rely on you knowing the direction of the magnetization of each nanomagnet. But what this nice work from Trondheim showed is that actually you don't need to know the direction of every nanomagnet. You can kind of take a coarser image and you can still get quite nice computational properties. So this is all simulation work. And so the question is kind of why has no one been able to do this in experiments so far in artificial spin systems? And I think it's probably because there's a lack of a rapid readout. And so the question is, can we use our FMR readout to probe the dynamics of the system and to perform computation? So I'm going to skip through this bit as Jack has talked about this. So one point that I should go on is looking at this figure here. So what we did here is we started our system in a few different states. So the top point corresponds to an all macro spin state. The bottom brown point here is a dense vortex state, and then some other states in between. What we first did is we applied a large positive field to convert some of the macro spin, so convert some of the vortices to macro spins. And we then applied some minor loops, so 15 minor loops, which is going to promote vortex formation. And so there's a few interesting things actually here. So the first part is that your response to the initial high field actually depends on which state you're initially in. So we're getting some nonlinear dynamics and some state dependencies. So it really cares about what state it was in before. The next kind of interesting thing is that the decay rate after you've initially applied a high field, it is different depending on your initial states. So again, you've got some history dependent dynamics here. And then finally, after a large number of loops, or so kind of when you're further away from the initial state, the system starts to converge and you forget what state you were in. And so this property is called fading memory, and it's a prerequisite to reservoir computing. So just to go over exactly how we're doing our reservoir computing here. So we're taking our raw input. So this could be a handwritten digit or some more simple like sine wave inputs or inverse saw waves. And so for each point on this sine wave, we're applying a minor field loop. So it starts off here at maybe 21 millitesla. So we'll go plus 21, minus 21. We'll then measure the FMR spectra, either in zero field or a slight bias field. Either in a slight bias field or at the field we just applied. So just go through here. And we're then going to separate our outputs. So we're measuring between 2.6 and 9.5 gigahertz in 20 megahertz frequency bins. And so we're taking the amplitude of the spectra at each frequency bin as a single output. So we get a total of 345 outputs. And so we repeat this process for every point on this curve. So we start at 21, we'll then do plus or minus 22, plus or minus 23, and we'll measure each time. And we basically end up with this kind of matrix of outputs. So we have our FMR spectra along the top and for each time point. So once we've kind of gathered all our data, we then do the offline prediction. So the goal here is to assign each of these columns a weight such that the the sum of the weights and the outputs will match this target data set. So here there's a square data set. So yeah, it kind of follows this matrix equation here. We're going to multiply this output by a weight vector, and that will give us our ASVI prediction. And then we're going to apply that to a test data set and evaluate the performance there. So the first task that we decided to do was this waveform transformation and a chaotic series prediction. So again, we've got our state here. We're applying a field such that the wide bars are flipping and converting to vortices, and our thin bars are not flipping at all, so they're remaining static. And so we're going to input a sine and an inverse saw wave. And the goal for this initial task is to do linear and non-linear transformations of the inputs. And this is quite a nice benchmarking task to kind of show that your system possesses the necessary non-linearities for you to do some computation with. And then we'll look at the prediction of a chaotic time series. So just to play you a quick animation of how this looks. So we've got the input field on the top and the spectra on the bottom. So you can see you're getting big shifts in the macro spin peak. You're also seeing this vortex mode pop in at low frequencies down here, and you're getting slight subtle shifts in the thin bar mode. So to have a look at some of the results from this. So like I said, we've input a sine wave, and here we're trying to use that to transform this sine wave into a saw wave. So just to explain what's going on the left, we've got the training data set. And so here is where we kind of assign our weights, and we use a linear regression to work out our weights. And then we apply the weights to a test data set. And so the target wave is in the red dotted arrow. The prediction from the artificial spin ice is the black line, and then the raw, and then the blue curve is the same prediction when you've bypassed the reservoir. So you're just performing the prediction on the raw data. As you can see, the raw data method fails completely. And so it's quite important to show the comparison between these. So, you know, it's really no pre-processing that's made the prediction work. It really is the reservoir that's doing the heavy lifting here. So here it is for a saw wave. Saw wave, it matches quite nicely. We've also got a square wave. Here I'm showing sine squared. Perhaps doesn't perform as well, but I'll show you some tricks that we found to improve this later on. And then this kind of non-linear transformation, which depends on your previous inputs. And so you can see we're getting fairly decent prediction performance here. So it kind of shows that we possess the necessary linear and non-linearities in the microstate trajectories of the ASI. So next we wanted to do some chaotic time series prediction. And for that, we chose the Mackey-Glass equation. So this is a commonly used benchmark in reservoir computing. And so your aim here is to predict the next time step, the value of the next time step, or 10 steps into the future. And so you can see that we get quite nice performance, especially for the future step, the input looks fairly similar to the target value. But when you go 10 steps into the future, you can really see the difference between the reservoir performance and bypassing the reservoir. And then just to show you how this looks across all the future steps, for the ASVI, we get a fairly flat profile on the error between the target and the prediction, whereas for the input, you get this kind of periodic behavior, and that's due to the underlying periodicity of the Mackey-Glass equation. So I should say that here we're using quite small training data sets, and we chose this because, well, for two reasons. One, because we're actually measuring this on quite a slow setup at the moment, so data acquisition is limited, but it's also suitable for kind of environments such as space or in your phone, where you don't want to use a lot of memory and you don't want to use a lot of processing power. And so having these short data sets is an advantage in these applications. But when you increase the training length set, we can improve our performance, up to 3 times for these transformation tasks, and up to 2 times performance for the Mackey-Glass equation. So we then went and had a look. So we're using a subset of our outputs in these tasks. We're basically cropping the 2 main peaks, the macrospin and the vortex peak, but we wanted to see what would happen if we were to optimize which outputs we use. So for this, we're starting with all of our 345 frequency bins. We're then randomly adding and removing outputs until our error reaches a stable point. So an example of how this looks, we've got our error on the right here. And as we continue our optimization, our error reduces. And what we actually found was that different parts of the spectra really help for different tasks. So here we've got the various transformation tasks to show you. And the original FMR response is the black curve, and then the red dots are the weights that ended up being used. As you can see, it really does change between tasks. And again, this is kind of demonstrating that we have a rich set of dynamics in this system, and you can harness certain parts of the spectra for different tasks. So that was all measuring in a small bias field, but we wanted to look at what would happen if we measured at the applied field that we just input. And so just to show you how this looks, you're still getting your reduction in peak size, but you're also getting the shifts that follow. You're also getting kind of linear shifts that follow these mode profiles as you go through the field. And so here you're kind of combining a nonlinear reservoir with, in terms of your state dynamics and how the state's changing, and you're also getting this linear part of the mode profiles. So to compare how this, so just to show you the effects of this, here on the left we have the original plots that I showed you, and on the right is this new measurement scheme, and we actually find an improved performance in all tasks, which is particularly notable in this sine squared task down here. But before we really didn't perform too well here, but now we see an order of magnitude improvement in the prediction quality. So that was all done on the sample that Jack showed you, but then we wanted to see, okay, is there something special about this sample, or can we apply this to more generically to other spin systems? So the first thing we wanted to try was, okay, can we measure in the other direction? So we change the direction of the thin bars So yeah, this is the same sample, just yeah, the tin bars are in a different direction. And then on this, we have a separate width modified sample, which has a weaker interaction and doesn't show vortices. And so, yeah, I can just quickly play these different spectra response. You're getting quite different changes depending on which sample you use. We also have a normal square sample. So this is where all the bars are the same, and we don't see any vortices at all. And just to show, I'll just pick one of these to play. We're still getting reductions in the macrospin peak, and that's due to just demagnetization, but we're seeing nothing in the vortex region here. So just to compare how these different samples performed, we have the original sample in blue, and then the other orientation of that sample, and then the weaker interacting. And so kind of as we'd expected, the originals sample has the richest dynamics out of all of these, and we see the best performance in this, and that's followed by the other orientation, and then the sample with weaker interactions and kind of no vortices. So it's kind of as we'd expect, and this is consistent across multiple tasks. Okay, so yeah, so this was just with the 3 width modified samples, but when you add the square sample with no width modification and also no vortices, we actually found that this has a much better performance. And so we're still trying to figure out exactly why that is, but it's a hint that maybe the vortices aren't necessary, and you can really apply this to kind of any spin system that you want. So now we have kind of multiple data sets across multiple samples. We can start to think about the idea of combining multiple reservoirs in one system. And the reason you'd want to do this is because your different reservoirs will respond on different timescales for to different tasks. So this could be particularly important for like the Mackey-Glass equation, for example, where you have a kind of chaotic spike on top of a periodic waveform. But just to show you an example of this, so here is the original sine square prediction from the original sample that Jack was talking about, and that I've been showing you. It's really not that good. But then when you combine it with the different orientations or different samples, we start to see gradual increases in the performance. And so here we've gone from a really quite bad prediction to a much better prediction. And yeah, I think the best one is when you combine all 3 of these reservoirs that respond to different timescales, you're getting a quite nice prediction here. So that's kind of where we're at experimentally, but we have some preliminary results that suggest we'd be good at some of the more complex tasks. So we created a really simple model where we were just modeling the macrospin peak amplitude, and we were just using some plots from here. It's quite a basic model. It probably doesn't capture the physics very well, but we ran this handwritten digit data set through it. So it's a commonly used data set in neural networks and things like that. We applied the fields, modeled how the macrospin peak behaves, and we found up to 85% recognition rate. So here's your input 0 to 9 in digits and your output prediction. And what you're aiming for is a nice diagonal here, so which shows the strong prediction quality. So just to conclude, we've shown that the artificial Spin-Vortex ice and the FMR readout is actually quite a good way of doing this reservoir computation. So we've got the necessary nonlinear dynamics, and we've also got a rapid readout enabling us to probe the state. And we really showed some nice results where, okay, you can start to combine multiple reservoirs to increase your performance on more complicated tasks. And so what we're kind of moving forward to look at now is, how can we speed up what we're doing currently? So yeah, we're currently quite limited by data acquisition time, so we're looking to improve that. We're also looking to do these more task agnostic metrics, which really allow you to compare different reservoirs across different systems. So not necessarily just spin systems. And so you can really evaluate how much memory your system has and things like that. And then we'll look to use that for more complex tasks, such as image and voice recognition. Great, and that's everything.
Thank you very much. Thank you, Kilian and Jack. It's very, very interesting. I'm sure we have a lot of questions. It might be the case that we still need to see one of the slides. Yeah, thank you very much. Great talk. So let's open this for questions and discussion. Anybody, you can use the chat or you can just ask the question. I will start with a bit of a technical question. So you mentioned you are limited by the data acquisition time. And so I'm just trying to see what is the limitation there and how long would it take to run one whole thing? Are we talking about, many hours? Are you limited by how fast you sweep the magnet? What's sort of the technical thing?
Yeah, so we're currently taking our measurements in a PPMS. So we're using a superconducting magnet to only go up to 30 millitesla or something. And that's just because it's compatible with our current FMR readout. Mm-hmm. Really, we could use an electromagnet and a VNA type of thing. And so we could massively speed up there. We've also got some ideas of maybe a bit further down the line where we could use kind of nanosecond pulse field inputs and stuff like that. But I think the first step is to just get us into kilohertz speeds rather than minutes for one measurement. Okay, so kilohertz would be what you try to do next. And this, so it comes from the method and not from, so how fast inherently would the system be able to run? Is there a way to estimate that? Or?
Yeah, there is. And it's actually something that we've been thinking about quite a bit recently in a response to reviewer comments on the paper. So I've just written a section on this and luckily it's fresh in the mind. So our group has previously got magnets to switch using pulses down a strip line. So if you imagine your spin ice array here, you've got a strip line here. There's no reason why that couldn't be wider, or you couldn't have several, basically the more texture you can get to your reservoir, the better they work. So you can imagine having, several strip lines across an array, or even like a grid of them. Okay. We can put pulses as low as 5 volts for as short as 20 nanoseconds to get our magnets to reverse. Another group, so there's a Stuart Parkin paper that was also looking at artificial spin ice that used a similar trick. They had a nicer pulse thing than us, and I think they pushed it further. We really weren't in that study interested in taking it as fast as it could. They achieved the same with 3 nanosecond pulses. So in the simulations where I showed you of our max spins and vortices converting back and forth, that's on the 1 to 2 nanosecond scale. The spin wave dynamics are also on similar scales. So, you're looking there, and that's, without really pushing it to change the shape of your magnets or the materials. To speed that up, you're looking at hundreds of megahertz. And, I think there's no real reason why you shouldn't be able to take it right up to those gigahertz scales that are intrinsic of the reversal and of the spin waves.
Okay, that's very, very interesting. We have another question from Michael, who needs to leave, but still wanted to ask the question. Could this be applied to different spin ice lattices, like Kagome, something like that? Yeah?
Definitely. Yeah, definitely. So the benefit of the square is that there's a geometry where you apply a field at 45 degrees to both bars, where they get an even share of the field. The issue with Kagome is it's tricky to get them to all have the same coercive field. However, our thinking on this system is still admittedly quite naive, and it may well be beneficial that you can have a broader field range where in one side of it, one subset of bars is reversing, at another side, another subset is. So we already kind of have that with our thick and thin bars. So going to something like Kagome or even the Penrose thing I showed, or Pinwheel, we're quite interested in. There's really no reason why they wouldn't work.
That's very, very interesting. Okay, so, and, of course, it's a discussion. So, Kilian, Jack, or Will, or Hide, I think he's still in. So anybody who can contribute or would like to contribute. Any other question?
Yeah, Christopher, so thank you both, Jack and Kilian, for really a very, very nice talk, a very interesting talk. The question I wanted to ask is, you're in creating the vortex states with this field cycling procedure. What's the role of thermal activation in all of this?
So we think that temperature does play a role. So I think we tried to do some initial simulations on the vortex formation process in Mumax, and we couldn't really get them to work until we included temperature. But the truth is we haven't looked at it fully, and it's something that we plan to do. So there's there's some nice work out there that's showing if you can be at the kind of temperature where things start to get chaotic, so whether that's in your vortex formation, then your reservoir computing properties can actually work much better.
Yeah, so because you showed a very nice graph of the difference in the delta energy states, which was sort of in attojoules. Well, that's a lot less than thermal energy typically, and you see this in magnetic systems where you get this. Effectively, you can change the state gradually because you apply effectively a field or a set of stimuli that are just below some sort of threshold value, and then you allow thermal activation to take you over, and that seems to be the sort of heart of the physics of what's going on. At least, I put that as a question, not a statement.
It's something that we're interested in, and we're quite lucky that our FMR system can operate at a range of temperatures. Right. So we're actively pursuing that.
Okay, that sounds really interesting. What size bars did you have when you for your wide and narrow, but how long, how wide, how thick?
So these ones, and it's important to state that it currently represents an unoptimized system.
Yeah, no, I understood.
Yeah, of course. So the length is 600. The wide bars are 200 wide, the thin bars are about 110. Okay. And the gap between the tip of each bar and the center of the vertex is 90, 100 nanometers around there.
Okay, so have you tried to think about what happens when you get small variations? Because lithography at that level is not going to be absolutely perfect, even if you've got a really nice system. You
definitely
have some imperfection.
We think that the quench disorder, so what I was describing earlier in my talk, where your bars are all different, and we know that for sure from the distribution of coercive fields that we observe, it helps you. So there's a lot of research on other reservoir systems, so whether it's a memristor or a spin-torque oscillator, the greater the distribution of dynamics you have in your individual elements of your reservoir, the better the performance, because they're more able to capture different timescales, a broader range of nonlinearities. So for sure we have it. We've had to pattern these arrays on a millimeter scale, which has been very challenging.
We're aware of that for a completely different idea, but yes, I'm very aware of that.
So your e-beam can take 4 days, and you're going to have current drift. All of the things you would usually get that give you quench disorder, they're quite relatively extreme in this system, and I think it helps us.
Right. Okay. Interesting. Thank you very much.
Okay. Thank you. We have a question from William. Will.
Hi. Yeah. Firstly, thank you again for a really, really great talk and some really impressive work. I wondered if you had any ideas for how you might sort of miniaturize the readout of this system. Obviously, it's fantastic that you don't have to read each element individually, but you've still got to use a VNA, and it's still quite a sort of a cumbersome method. I wondered if you had any ideas about how you might sort of read the microstate of this system without having to do that.
Kilian, do you want to take this?
Yes. So obviously we're using quite big waveguides and things like that. So one option that we've been thinking about recently, well, there's a few options. One, you could kind of have your kind of micron size waveguides to probe the entire response, or you could have individual kind of high Q resonators just kind of located at different areas of your sample. So I think just kind of, rather than using these bulk waveguides, if we can actually pattern the readouts on the chip, then that already goes some way to improving the scalability there. Yeah.
I think it's worth saying that we actually don't use a VNA here. It's a far simpler diode-based method, and those things have been miniaturized. So there's no reason why you couldn't have an RF generation source. So we're using a broadband one here. you could use a resonator. So, you know, your RF generation would look like the strip line I described earlier. So the same fields that we would use to switch things, you know, if you're putting a 3 nanosecond sync pulse through that wire, you're getting RF excitation out of your magnets. And actually, when we simulate these things, we simulate them with those type of nanosecond scale sync pulses. So that's, you know, that's a kind of solved issue to some extent in the nanopatterned electronic side of things. And then, like Kilian says, you know, you can make these resonator waveguides. So rather than being total strips, they'll come down. You have a little circle. You can tune that to different frequencies. So, you know, you could see that from our spectra that, you know, it's a lot of just kind of noise and ripples and then some big peaks. Mm-hmm. So let's say you had, and again, saying this thing about the more texture spatially you can put into your readout, the better. So you know, we're picturing you'll have something like 100 by 100 microns of spin ice, perhaps smaller. You know, we're way above the scale where, you know, adding more magnets, it's not helping us, we're saturated. And then you could have along the edges resonators at the different key frequencies patterned. You excite through the strip lines and you lock in to, you know, you'll get a very pure signal because these things have such high Q values, and you measure just through a diode.
Great, thank you.
Okay, so if anybody else has any questions, please prepare the question. In the meantime, from the part, sort of not of the physics, but the learning and the applications, I noticed that in the end, you showed the MNIST digit recognition. Of course, this is something that we absolutely all need to show. It's a commonly accepted metric. And then you mentioned that you would consider expanding it in image recognition or speech. So while watching the talk, I was under the impression that this would be a technique that is better for temporal dynamic signals, medical signals, ECG signals, rather than image recognition. But I could be wrong. Could you discuss that?
Yeah, I completely agree. I think I guess the problem with image recognition is you have to convert it into some sort of time series beforehand, whereas I think you're right. I think these reservoir systems are much better suited for things like medical things, you know, ECG signals, you know, where you can actually have a device with it in.
Yeah, exactly. That's what I would think. Yeah, it would be ideal for such a sort of low energy, you know, edge computing application. Anybody has a question?
There's one comment on that I found interesting. So the Mackie glass, which we run prediction of, it's a mathematical model that was created to model the relative changing values of certain hormones in the blood. So you can imagine something like an insulin pump or a other hormone regulating device that's embedded, and you have these kind of interacting systems which are quite hard to predict, and you'd have an embedded reservoir system which, you know, would be doing a kind of more exotic PID to try to regulate the dispensation of certain hormones or other things inside the body. I think that's one really promising use case.
Of course, I have a lot of questions, but we need to be conscious of time. So I will ask, you know, if anybody has any last question and last comment. Allow me to ask something about Kilian mentioned the role of the reservoir versus the pre-processing. And could you show that slide again, where you show that the pre-processing is not doing anything, but it is the reservoir? I mean, could you comment a bit more on that, or how would you quantify the role of the reservoir? What it actually does there? And in the meantime, if anybody has a last question, we will proceed with that.
So what we think is going on here, so yeah, just to nip back here. So basically, like what we're doing when we're showing the inputs is we're just taking the raw input and we're trying to update the weights on it. And so the problem is that here you only have one value for each point. So you really can't do any training on just one value. You can only do a multiplication of it. Whereas we're kind of projecting that into this kind of frequency space here. That's giving us lots of different readouts. And what we think is going on is that basically the different parts of this readout are introducing different harmonics of the input data set. And so that's why we're able to do these transformations really quite nicely. So that's for the transformation stuff. But for this Mackie glass stuff, you can't just rely on kind of nonlinearities. You really need some memory to be able to predict. You really need to learn about the past to be able to predict what the future is saying. And so this is really kind of showing that our microstate trajectories, the memory associated with that is really helping here. So it's a kind of combination of projecting the harmonics as well as the memory coming from the ASI. I think that's kind of what we think at the moment.
Okay, perfect. Thank you very much. In order to be conscious of everybody's time, please let me know if there's any sort of super urgent final question. I don't know if Will, if you would like to make a comment or sort of final statement.
Thank you, Christopher. So just to follow up on what Kilian just said, I think the most important thing, and maybe why we show those things, which just look like sine waves, is that we were new to reservoir computing, and a lot of the benchmarks we found in the literature, our reservoir worked fantastic for. But then when we tried just doing the inputs and the post-processing without the reservoir at all, it worked just as well. So these like wave transformations are sort of the simplest benchmark we could find where, a simple linear regression thing does not work. So we think it's actually really important to show that what you're doing in the software, can't solve the problem on its own. And that's actually absent from a lot of the publications you'll see on like reservoir hardware, which, it really shocked us when we realized that actually these tests weren't doing the job, or, there weren't tests which discriminated what the reservoir was doing from what the linear regression did.
Which is what I found very interesting in your work as well, but it made me think about it, and the actual reservoir, which I think is quite unique.
Yeah, because we read a lot of papers before doing it ourselves, and we just didn't understand that at all. Until you do it yourself, you don't realize how powerful like regression really is and how many things it can solve. So,
absolutely, this is really I thought it was one of the key aspects.
It's all about putting non-linearity in the system. I think basically it's not to say that there's no software out there that can do that, but you certainly really are transferring a lot of the computational work onto the reservoir when you do these like non-linear transformations. So that's where the hope for applications is, I think, at least in the short term.
Okay, thank you very much. In order to respect everybody's time, I hope we have more discussions in the future. Thank you very much to Kilian and Jack for the wonderful work. Thank you very much to Will for joining us. Thank you to Hide for joining us. And thank you, everybody. Thank you very much.
Thanks. Bye, everyone. Thanks for inviting Kilian and Jack.
All right.
Okay. Thanks very much.
See you.
Cheers. Bye.
Bye. Thank you.